All right, so the first substantive lecture that we've got, we're going to introduce a new term, stress, which we're going to be using pretty much throughout the entire term. Stress is a way that we quantify the intensity of the loads, the forces and moments that we calculate from statics. So we take those forces and moments like normal force, shear force, bending moment, things like that, and then we identify how much intensity those cause at a specific point in a member. And you'll see this with the diagrams, it'll start to make a little bit more sense. So stress is a very important term. In chapter 2, we'll learn about strain, which instead of trying to quantify the effect of the loading, strain is really trying to quantify the effect of a change in geometry. So stress and strain, both very important aspects of this class because it allows us with then chapter 3, material properties, to identify the relationship between stress and strain for specific materials. And then that allows us to estimate the change in, let's say, the deflection of a beam due to a given loading. Once we're able to relate the stress, the intensity of the loading at specific points of a member, to the strain, which is the change in geometry at the same point. Then we use calculus to integrate, and that makes life a little bit easier. So let's go ahead and introduce this concept of stress. So this chapter, we're very much focusing on average stresses in chapters 4 through uh, 8 and 9. We'll be looking at more specific and kind of robust ways of calculating stresses, but for now we're introducing the term and the concept, and we're going to be doing very basic type calculations, but just something to keep in mind in the back of your head that this is a very simplified procedure for average stress, and that we'll be doing more precise procedures a little bit later on. So, what is stress? Well, we want to go back and review a little bit of statics first so we can figure out what the purpose of calculating a stress is. So you'll remember from statics that a lot of the workflow is simply looking at a system that has some external loading on it, and then we try to figure out how that load transfers to the supports. So the external loads can take a bunch of different forms. We have concentrated forces. We've got forces that act over an area or are spread out over a linear distance, or we've got body forces like forces accelerated by gravity. All of these we need to be able to quantify. Oftentimes what we do in statics is we turn these into a single resultant force, as you see with F sub r right here. That allows us to look at the effects of those forces more easily in terms of mathematics. And you'll remember from statics that those support conditions are the location of some unknowns. So depending on how our member is supported, whether it's a cable or a roller or an external pin, that ends up being the source of multiple or possibly multiple unknowns that we're often trying to calculate in statics. So with a cable, for example, we have one unknown force. It's only one unknown because the magnitude of the force is unknown, but because it's a cable, we know the direction of the force. Whereas like with a pin, we have two unknowns. It's both the magnitude of the force and the direction are unknown. So you can represent the reaction of a pin as a single resultant force with some unknown angle, I'll call it theta here, whether you represent it as Fx and Fy, or whether you represent it as an unknown angled force with an unknown angle. Either way, we have two unknowns. All the way down to like fixed supports where we have three unknowns in a two-dimensional system. And the touchstone for these is really if the support is preventing a translation, that means that it can induce a force to prevent it from moving. And if the support is preventing a rotation, then the support is able to produce a moment to prevent that rotation. So just to kind of refresh our memories, a pin support like we see in the upper right, that pin doesn't allow the beam to move up and down, and that's why we can get a vertical force, and it's not allowed to move left and right, and that's why we get a horizontal force. Now, this beam is free to rotate about that pin, and therefore rotation is not prohibited, and therefore this support cannot apply a moment to the beam. Whereas with a fixed support in the bottom right-hand corner, a fixed support prevents the beam from moving up or down or left and right, and that's why it can have a vertical force and a horizontal force, but it's also not allowed to rotate about that point, and therefore we can induce a moment, or that support can apply a moment to the beam. And that's why we get three possible unknowns. Something else to remember about these support conditions, these are all possible support conditions. Some of these might end up being having a value of 0. So it's very common for us to see one of these force or moment reactions be equal to 0. This is just mapping out all of the possible forces and moments that can be applied by the support to the beam itself. All right, and a little bit more refreshing of our memory of statics. I mean, the fundamental basis of statics is global equilibrium, or just equilibrium in general. When we say static equilibrium, we mean both that the body is not in motion and it's not accelerating. So oftentimes we just call it equilibrium, which simply means that there's no acceleration, but static equilibrium means it's also not moving at all. So either way, the important takeaway from that is that because there's no net acceleration, the sum of all the forces and the sum of all the moments taken about any axis or in any direction have to be equal to 0. And we use that as a calculation tool to then be able to figure out the unknown forces based off a free body diagram that we create. So the basics of that, you see the amorphous kind of blob body on the right-hand side. If we have multiple forces applied to that body and we were to make a section cut anywhere that we want through the body, we can remove everything on one or the other side of that section cut, and then there will need to be forces and or moments transferred across that section cut to keep everything in equilibrium. And that's a great tool that we have in statics. That section cut, we're not physically cutting it, we're kind of using like an X-ray to cut it and then figure out, well, if we were to replace everything on the bottom with some equivalent forces and moments, what would those be? And that is the amount of force or moment that is being transferred by the material through that section cut itself. So here's an example. We make that section cut through the body. Now in reality, the way that the forces and or moments are being transferred across that body, it could be a large array of differing kind of vectors of forces, different directions, different magnitudes, spread out all over that section cut, and not necessarily spread out evenly, but different small amounts of forces kind of all across. Well, in statics, we usually simplify this down into a resultant force and a resultant moment. That's just a vector sum of each of those. So and a vector product. So we take all of those forces in their different magnitudes and directions, we sum them up to get the resultant force, and then we use the basis of how to calculate a moment to figure out the net moment. And then each of those can be represented by a vector. So we have a moment vector, we've got a force vector acting through the centroid of that cross-section cut. But we usually want to simplify, or at least, I'm sorry, break these resultants up a little bit more in a way that is easy for us to kind of bookkeep. So we've got a resultant force at some angle. We've got a resultant force at resultant moment at some other angle as well too. But what we often do is we try to break up those internal resultants into specific directions relative to that section cut. And this is going to be critical for us when we start calculating stresses, because the stress based off the force that's acting perpendicular to the section cut is going to be calculated differently than the stress due to the force acting parallel to the section cut. So it's all about whether you're looking at something parallel to the section cut or perpendicular. Another word for perpendicular is normal. And so here we can see that if the section cut is right here, the normal force N is acting perpendicular to the section cut, and the torsional moment, the moment acting about that axis perpendicular to the section cut, those are both like normal projections. And then for the projections that are parallel to the section cut itself, we have a shear force V, and we've got a bending moment M. Now in 3D, we can even break up these parallel projections into further orthogonal projections like a shear force in the Y and in the X direction, but we'll get into that when we get into 3D a little bit later on. Suffice to say, statics alone with this diagram right here, we could use statics and a basic free body diagram like this to be able to calculate the normal force, shear force, torsional moment, and bending moment acting on this section cut. And that calculation tells us N, V, T, and M are being transferred by that material where we've made that section cut. So because it's being transferred by that material, that means that these forces and moments are going to cause, you could just intuitively figure out that these are going to cause some um, movement or deformation of this body. And that's really kind of where we're going next as well. We want to be able to quantify the intensity of these loadings acting on this cross section. Once we figure that out, we can use some knowledge about material properties to then estimate how much is that body going to deform. And we do that on like a section cut by section cut method, and then we'll use calculus-based techniques to then integrate it over the length of a member. That's kind of where we're going with this. But at this point, really, we've just only talked about statics. I mean, calculating normal force, shear force, things like that. We've done all that in statics before. This is just a refresher. Now in 2D, life's a little bit easier. Similar kind of a diagram. We've got a body. We make a section cut where we want to figure out what the forces and moments are being carried by the member. We make that section cut. We show the possible internal resultants, N, M, and V. No torsional moment here in a 2D system. And then for this, I mean, this would just simply become our free body diagram, right? Show my coordinate system, use equilibrium, and those three equilibrium equations along with a proper free body diagram would allow me to calculate V and M and N based off geometry and these external loads. I mean, that's the fundamentals of how we use statics to figure out the internal resultants on a section cut. We use a similar process to calculate the support reactions as well. Just with the support reactions, we don't really make a section cut through the body itself. We're simply looking at the external supports. But the same exact procedure allows us to use equilibrium to calculate both external support reactions or internal resultants like normal force, shear force, and bending moment. So just to refresh our memory, we may need to calculate support reactions first if we're trying to use the method of sections to figure out the internal resultants in a body. Maybe we do the support reactions first. This would be done with a global free body diagram. That simply means no section cuts. So you look at the entire system, you don't make any section cuts, you replace the support conditions with the unknown support reactions, and then you use equilibrium for the entire free body diagram to calculate the support reactions. That's just statics 101. And then you would, once you have your support reactions, if you need them, you would then make a section cut where you want to figure out the internal resultants. You would choose one or the other side of that section cut and replace everything on that side that you chose with the unknown internal resultants. In 2D, that would be N, V, and M. And then you just use the equations of equilibrium with that new free body diagram with the section cut and the internal resultants. You would use that to solve for your internal resultants. And we'll go through an example to kind of refresh our memory of that. Now again, this is still just statics at this point, and you might say this kind of sounds familiar, possibly, or maybe you feel really good about this. Either way, this is just, for PSU classes, this would be EAS 211. This is fundamentals from statics, internal resultants, support reactions, things like that. So you might need to brush up a little bit on your memory. So there will be a separate video walking through this example on how to calculate internal resultants. So you can look up on the playlist, and this will be the first example that I'll walk through just to remind us of how to go through the process of global free body diagram, equilibrium to solve for the support reactions, and then making a section cut, using that section cut to create a new free body diagram that shows the internal resultants on one or the other side of that section cut, and then using equilibrium again to figure out the internal resultants along that section cut. So here it asks us to figure out the internal resultants acting on a cross section through C. So basically we choose either everything to the left of C or everything to the right, and then we replace it with just the internal resultants NV and M. So take a look at that video if you're a little bit rusty about this, but that'll be a separate video from here. We'll do that mostly with the example videos. I'll go through the lecture, you can pause it whenever you'd like, and then I'll have separate uh, example solutions that you can take a look at on the playlist. I also want to point out that there are PDFs of the fully worked out solutions up on D2L as well. So there are these nice annotated workout solutions that are basically the same exact thing as what's in the video. People just sometimes learn differently. Some people prefer to have it all laid out in like an engineering calculation to study from. Some people prefer to watch the video. It's however you learn best. I want to give you that flexibility. All right. So now that we've refreshed our memory a bit about internal resultants and the statics of it all, that's often going to be the first steps that you do for most of the problems in this class, the statics. And now we're going to actually talk about the strength of materials or mechanics of materials part of it. So here, just to kind of give us a roadmap of how statics hands off to mechanics of materials, um, statics allows us to use geometry and equilibrium to calculate support reactions and specifically the internal resultants acting at any location along a beam that we're interested in. So those internal resultants are what we were just talking about, like normal force, shear force, torsional moment, bending moment. What mechanics of materials allows us to then do is to calculate the internal stresses due to those internal resultants. So like we saw before, the internal resultants are kind of a broad summary of what's happening on a cross section. Uh, on the cross section through a member, um, the normal force is just the sum of all the forces acting parallel or sorry perpendicular to the section cut itself, um, and the stresses are more specific to like a location on the cross section. You'll see this in a second, but the internal stresses writ large are simply the intensity of a loading of an internal resultant at a specific point on the cross section, and it might change depending on where you are on the cross section. So it's like the internal resultant is like the forest, and the internal stresses is like an individual tree in that forest. It might have a different size, a different shape, and it's just one small part of the larger kind of forest. Once we're able to quantify what those stresses are, and we'll do that in just a minute, then we can start calculating or estimating what the strains are. And I mentioned at the very beginning of the lecture that strains are the quantification of the deformation of a, a part of a system or a part of a body. So we'll look at like a very small piece of a material, and the strain is simply how much is that getting longer or shorter, how much is that changing its angle. Well, stresses and strains are related based off material properties, and so if we understand that relationship, we can go from basically all the way back from the loading and the geometry of a system to the stresses and then eventually to the strains. We can start estimating what the change in overall geometry of the system would be, and that's what we call global deformations. So one question that we would often ask would be, all right, I've got a simply supported beam like this, and I put a load of some amount, and we're given what the geometry of the system is, and we're given some material properties. The question would be, how much deflection does this beam undergo? That's what we would call a global deformation or deflection. And strength of materials, mechanics of materials allows us to kind of go through that entire process from loading, geometry, material properties, all the way to calculating the change in deflection, for example, of a beam. The other thing that we can do is determine whether or not a system would fail. And this is really where like the strength of materials comes into play. When we say failure, that could mean a bunch of different things, but typically we mean the material physically like separating or crushing or breaking or cleaving, anything like that. And the failure theory is often the inputs into these four different theories that we'll talk about in chapter 10. Often the inputs to that are simply the internal stresses acting on a specific cross section. And it's a lot more complicated than that. We have to look at what's called stress transformation and principal stresses. But again, the question of how much does a beam deflect and will this beam break? Those are the types of questions that we can start to answer in strength and materials. So we take what we learned in statics to get the internal resultants, and then we hand it off to these techniques that we'll develop here in strength and materials. But that's where we're going with this material. So we have a lot to talk about. Stress is what we're talking about right now. Strain is lecture 2. That's the quantification of the deformation of an element or a body. Material properties relate stress and strain to each other. Every material has a different relationship between stress and strain. Some of them are nice and linear, some of them are nonlinear. We'll have to talk about that and the different phases of material behavior under loads. And then we'll get into some very specific types of loading. So chapter 4 is all about just axial load. So columns subjected to an axial load. How much do they deflect? What is the stress? How do we deal with statically indeterminate systems where static equilibrium alone is not enough to figure out where the forces go? That'll be, I believe, chapter 4. Chapter 5 is torsion, so shafts that are subjected to twisting. Chapter 6 is bending, so um, members subjected to a bending moment. Shear is mostly beams subjected to a internal shear force. And then combined loadings in chapter 8 is where we'll take multiple types of loads, axial loads, bending, things like that, combine them together and see how that affects the stresses. And then in chapter 9, we'll talk about stress transformation. That's like, let's say that we had a tank with a weld oriented at 45 degrees. Usually we would calculate the internal resultants for a 90-degree cut through that member. And so how do we transform that to give us the stresses oriented with that 45-degree weld? That's a pretty interesting technique. We'll talk about failure theories, how to estimate whether or not a member will fail at a specific point, and different materials behave differently at failure. So we'll talk about ductile members, brittle members. That'll be a big discussion in chapter 10. We'll skip a chapter, then we'll get into chapter 12, which is beam deflection, which is where we'll actually start to calculate the estimated deflection of a beam. Due to bending moment, there's some big simplifying assumptions that we have to make, but that's a pretty interesting differential equation derivation in chapter 12. And then once we've covered deflection, we can then transition to column buckling. Buckling is a effect in a compressive member where if you have a column like a purely compressive member and you're just loading it axially, like force parallel to the long axis of the member, uh, there is a force, an amount of force P that will then cause that column to become unstable, where any little horizontal force would cause it to buckle out suddenly in a very kind of unexpected failure mode. And we want to be able to calculate what that is. It's called P critical. And in order to derive what that anticipated value would be, we need to understand how beams deflect. And so that's why this comes after the chapter 12 beam deflection. So a lot to cover, but the big themes that you're going to be seeing would be stress and strain is really inherent in almost every single chapter of what we're talking about here. So really need to get a good fundamental basis of what stress means. So good segue. Let's go ahead and talk about stress. So the textbook definition is the intensity of an internal force acting on a specific area passing through a point. So I think the big takeaway here is that stress is specific to one location on like an area. So if we're taking a cross section or a section cut through a body, when we're talking about a stress, we're talking about a infinitesimally small area, not the entire cross-sectional area of that cut, not like this kind of circle type shape. We're talking about a specific differentially small element that we're trying to calculate the um, force acting on that small area divided by the area itself. And so this becomes a limit basically. We're trying to figure out, well, as we look at a smaller and smaller area, the amount of force associated with it is getting, approaching zero because there's not as much area to collect any load, and the area is getting smaller as well too. So this becomes a limit where the area gets differentially small, which is what you're going to see on the next slide. The other thing that I want to point out from this slide is that um, we can think of this in terms of like a small three-dimensional differential element. You'll hear that term a lot and read it a lot in your book as well too. This is a differential element right here. So just to make the math more accessible, we typically break down things into orthogonal directions. So if we have a differentially small shape, we think of it as having like three different orthogonal directions to work with our Cartesian coordinate system. So here we have a y direction, an x direction, and a z direction. And that differentially small area for each direction just becomes a face of a cube. So here you can see this cube, and each face can have stresses associated with it. The force acting on that face divided by the area of the face itself. Now, you're going to start seeing these variables, these Greek symbols that we're going to be using constantly. Sigma represents the stress acting normal to the face of interest. So sigma x means the normal force, or sorry, normal stress on the x face of that differential element. For this same face, we can have stresses that are acting parallel, and those are represented by lower Greek symbol tau. So tau xz means the shear stress, the parallel stress, the force acting parallel to that face in the z direction would be tau xz, and then we also can have a separate shear stress tau xy. The x means it's on the x face, the face opened up to the x side of the cube, and then the z or the y indicate which direction that stress is acting. So you can think of these as kind of like forces, but the units are not completely different. The units are normalized to the area that it's acting on. And so that's what we're going to see next, is that the way that we calculate the stress, whether it's a normal stress or a shear stress, is the amount of force acting on that area divided by the area itself. But because we're talking about a point, we just keep on shrinking that area smaller and smaller. As we're looking at a smaller and smaller area, the force, the numerator is going to be getting smaller. The area is going to be getting smaller as well too. So that as this limit of the area approaches zero, we have to then get a smaller and smaller area. It's like differentiation or integration in calculus. Now, even though this is limit definition, the actual practical application tends to be quite a bit more straightforward, and we're going to simplify this greatly to start out and do some average stresses. But the big thing to take away here would be the units for stress would be force per area. So we have a new unit or dimensionality to deal with. And sigma is a normal stress. It's talking about the intensity of a force acting perpendicular to our point or area of interest. So here's our area of interest. The normal stress is acting perpendicular, and the shear stresses, tau, are acting parallel to that area. So we can represent on this differential element as many as 6 individual stresses for the entire 3D element. Um, and the reason why is for each face, we would get a normal stress, but on the back side, on the opposite side, the normal stresses are exactly the same. That's for equilibrium purposes. Sigma x on this front face is going to be the same as sigma x on the back face. So we have 3 independent normal stresses, one in the x direction, one in the y direction, one in the z direction. And it's a similar thing for the shear stress as well. Tau xy and tau yx, for equilibrium purposes, those end up being the same thing, as are the same shear stresses on the other 2 faces of that cube. So we have shear stresses acting on like 4 faces, but all those shear stresses are the same. And so we do that in the x and the y and the z direction. So we end up getting 3 discrete or independent normal stresses and 3 independent shear stresses. And so we can actually represent the state of stress of a differential 3-dimensional element with this matrix. It's called a tensor, and tensor calculus is something that's used in advanced mechanics of materials for future classes that you might end up taking. And so here in this matrix, you can see that like tau xy and tau yx are exactly the same thing. So we get the normal stresses along the diagonal, the shear stresses acting opposite of the diagonal, but this just represents 6 independent values. How do we quantify the units for this? So we mentioned before that because we're looking at force divided by an area, you could think of units like uh, pounds per square inch, newtons per meter squared. In the metric system, even though we're talking about force per unit area, we typically would represent the stress in terms of like what you would think of as pressure units. I mean, force per unit area is the same thing as pressure. In terms of dimensionality, they mean slightly different things, but we would represent it in Pascal or use metric prefixes to do kilopascals, megapascals, gigapascals, things like that. So I prefer this type of nomenclature, and this would simply be not preferred. Um, but you need to understand what the relationship is between the two. Same thing with the US customary system. Even though like pounds per inch squared, we often could represent it in a calculation, pounds in the numerator, inches squared in the denominator. It's much more common to reflect it in PSI or KSI or KSF or PSF. Using these abbreviations is much more common than writing out fully uh, kip divided by foot squared. So keep that in mind. Kips, again, 1 kip is 1 kilopound. It's a very common unit in engineering because we're often dealing with large amount of force and dealing with millions of PSI or millions of pounds at least isn't quite as common. All right. So now that we've got some idea of what stress is, the intensity of a loading acting on an area, both either normal to it, perpendicular to the area, or parallel to the area. Now let's get into a couple specific examples of what that would look like in terms of like a calculation. And we'll have a couple of examples too. One for normal stress and then one for shear stress. So first, average normal stress in axially loaded bars. So when we say axially loaded, that means 2 things. An axial load is just a force. So I'm just going to draw, let's say we've got an element right here. An axial load, if this is the longitudinal axis of the element, an axial load is a force that acts parallel to the longitudinal axis of that member, and it's just a force. So this basically means that any cross-section cut that I make, I will only have an internal normal force acting on that cross section. So axial load, we hear it a lot. It basically means it won't cause an internal moment um, in your member. So here's a pretty straightforward example. So here we're dealing with average normal stress. This is a simplified way of looking at normal stress as kind of an introduction. It really only applies when we're talking about axially loaded bars. So if we were to look at a very simple system, a circular bar with a axial load external P, if we were to make a section cut through it, our free body diagram, here's our section cut right here. This is basically our free body diagram. And again, if I was going through and doing the actual calculations, I could show a shear force, but it's going to be equal to 0. I could show a bending moment as well too. That would also be equal to 0. The only thing that we would be left with is an internal normal force that would be equal and opposite to the external driving force P down below. So I would get that just from a free body diagram and an equilibrium equation. You can probably, if you're pretty comfortable with your statics, figure that out just intuitively by looking at it. But I could figure out that N equals P and that V equals 0 and M equals 0 just by drawing a free body diagram and then using statics like the sum of the forces equals 0, sum of the moments equals 0. That would give me these conclusions right here. So for an axially loaded bar, the only internal resultant that we get is the normal force. And for a pure axial load, just an axial load, we can assume that there's a uniform stress distribution for now. So this is a big assumption that if we were to look at the distribution of the stresses on that cross section, you can see that all of these arrows here are the same magnitude. It doesn't change the magnitude whether I'm on the left side or the right side of this cross section. We assume it's a uniform stress distribution. So we assume that sigma, the normal stress intensity, is equal across the cross section cut. Now in chapter 4, we're going to revisit this assumption and talk about when it's valid and when it's not. But for now, we're making a big assumption. So you can think of this normal force acting on the cross section is equal to the normal stress. Well, think of it a couple of different ways. Think of it as the volume of this shape where the height is sigma and then the base is the area of our cross section. Think of that volume where the height is the stress and then it's acting over the cross-sectional area. That's the same thing as the force, because the height would be in force per unit area and you'd be multiplying it times that area, which is the cross-sectional area of the shape. That would give you units of force as a result. So the internal normal force has to be equal to, if sigma is a constant, it would be sigma times the cross-sectional area. So that leads us to, in this simplified approach, we can just calculate the average normal stress as the normal force divided by the cross-sectional area. Makes our lives really easy. So if we have a uniform stress distribution, then we can easily calculate the intensity of the normal stress. It's just the normal force divided by the cross-sectional area. And that gives us the right units. Normal force is in force, areas in area units, PSI, KSI, pascals, whatever. But again, very important to note that we're assuming that the stress, the normal stress, is uniform across the entire area. And this is exactly what you see in here. Now, this is a couple important points on here. Your book will often write down that sigma equals P divided by A. I really want you to drive the idea home that sigma equals N over A. Let's just put like a squiggle through that. It's really important to note that sigma, when we calculate it this way, is the internal normal force divided by the sectional area. P is usually reserved for an externally applied force. So P and N are not exactly the same thing. Now, in a lot of simplified examples, the external force P will be the same as the internal normal force N, but not always. So for example, what if I had a column that looked like this? If I had two kips right there, and I had one kip right there, and one, actually, let's make this even bigger. Let's do five kips here, and let's do four kips here. If I were to make a cross-section cut through here, then the internal normal force would be equal to negative 5 kips of compression. Over here on this side, N is going to be equal to negative 4 kips of compression. Now, the question would be, well, if I'm saying that sigma equals P over A, the question would be, well, which P do I use? Is it this 5 kips? Is this 1 kip or this 4 kips? Well, it kind of depends on where you're looking in the system. It makes a lot more sense to just use the internal normal force. So it don't ever just rely on the external forces. That's not what we care about. We care about the internal normal forces. That's really what matters. So your textbook kind of plays fast and loose with this. They'll look at situations where the external load is the same as the internal resultant, but it's not always the case. So it's really, really important to note that N is what we need to use, not P. Internal normal force is what matters, and that involves making a section cut, using equilibrium and statics to calculate N, not just relying on whatever numbers are shown for the external loads in the system. Also, I want to point out that we'll talk about this a little bit more in chapter 4, that if you look really closely at a member that's subjected to an axial load, depending on how that load is applied to the system, you might get kind of like a deformed end where there's a lot more stress in the middle of that bar than there is on the outsides. And so usually when you get approximately um, the diameter away from the end of a member, then things become pretty uniform. But up until then, you might get some significant amounts of non-uniform stress distribution. And we'll talk about that more in chapter 4, but that's just to drive home the idea that this assumption of uniform stress, normal stress, is just that, an assumption, and not always necessarily going to be true. We'll talk about that a little bit more. It's called St. Venant's principle. We'll talk about it in chapter 4. And the last thing that I want to talk about here is that for the normal force and for the normal stress, positive means tension and negative means compression. And the way that we um, do that is, or the way that we kind of keep that into our practice, if, let me draw another one in compression. The way that we keep that in mind is, let's say that I've got a simple bar here, it's in compression, but even if I didn't know it was in compression by looking at it, never try to figure it out just on your own. Never just look at a system and say, oh, I'm pretty sure this part's in compression, so I'm going to put a negative symbol for that. I'm pretty sure this part's in tension, so I'll put a positive symbol for that. Don't try to figure it out on your own. Just use a consistent practice so that you'll always get the correct answer and the math will give you the correct sign. So if I was to make a section cut here and then create a free body diagram, keeping everything on the left, then when I draw my internal resultants, when I'm replacing everything to the right of the section cut, always draw your internal normal force pointed away from the section cut. So if I assume that N, the internal normal force, is in tension, it will always point away from the section cut. So here I kept everything to the left of the section cut, and so pointed to the right would be going away from it. And that means if I have my coordinate system here, if I sum the forces in the x direction equal to 0, I've just said that I'll put everything pointed to the right as a plus, everything pointed to the left as a negative. Look here, I have 10 kips pointed to the right, so that's plus that 10 kips. That's just based off the direction of this arrow. And then I have n is an arrow pointed to the right. That was my assumption. That means that I'm adding whatever the magnitude of n is. And then if I just use algebra with this equation, I get that n equals negative 10 kips, right? Whether it's a plus or a negative in my equilibrium equation, that's just based off the direction I've drawn the arrow in my free body diagram. Now, I'm going to calculate that the magnitude of n is negative, which is fine. It just means that the actual direction is the opposite of what I assumed, which is no big deal. But if you always assume tension for your internal normal forces, then plus will be tension, negative magnitudes will be compression. It just takes care of it for you automatically. And I know that, yeah, for simple systems, you can figure out what's in tension, what's in compression, but we're going to get into much more complicated systems, and it's not always going to be quite so straightforward. So my strong admonition to you would be don't try to figure it out on your own. Assume tension, draw your internal normal force arrows, assuming tension, let the math work out what the actual sign is. At the end of the day, when you give me an answer, positive normal stress will be tension, negative normal stress will be compression. However you get to that, it's completely up to you. Okay, so then here's an example. There'll be a separate video for this for you to take a look at. This is just a basic calculation of average normal stress. And so we've got a turnbuckle here, a common assembly to connect two threaded pieces. Because they're counter threaded, it allows you to turn the turnbuckle to either tighten this up or loosen it up. Here, the problem asks us to calculate the average normal stress at two different locations. One location would be through the turnbuckle itself on section AA, and then another would be through the actual bolt itself. And so we have to calculate two different normal stresses. We know that the equation for sigma is n divided by A. And so for each of these, we need to figure out, it's kind of a bookkeeping exercise, like what is the internal normal force, what is the area? And for the bolt, it's pretty straightforward. You know the bolt's going to be carrying the entire force P, so it's just the normal force P divided by the cross-sectional area of that bolt, pi r squared, pretty easy to do. When you get to the turnbuckle, this is the cross-sectional view of the turnbuckle. You've got some rectangle on the top, some rectangle on the bottom. How do you deal with that? Well, you'll get to the right answer either way, but either you look at just the top or the bottom. That would mean that the force gets split in half. N becomes, you divide it by 2, and then you're just using the area of the top or the area of the bottom. Or you end up looking at both of those pieces together, the top and the bottom on that section cut together, use the full normal force N, and then you divide it by both the top and the bottom area. Now you get the same exact answer either way. That's the whole point of this, is that if I cut N in half, that's the same thing as doubling the area A. I get the same exact result. So I'll have a video to kind of walk through that, but this is just to identify that even though the normal force like is overall the same throughout this entire system, the area can change and therefore the normal stress can change as well too. So take a look at that video that I'll post on the playlist. All right, next thing that we've got to talk about is average shear stress. So we've been talking about average normal stress, the stress acting perpendicular to the cross-section cut. Now we're going to be dealing with average shear stress. So that is going to be the stress, the intensity of the force acting parallel to the section cut. Now, I do recognize that I say cross-section and section cut kind of interchangeably. I do want to take a quick aside just to make it really clear that if we're talking about a uh, member like this and with a longitudinal axis, almost all of our members that we're going to be looking at would be long, slender members because that's usually the assemblies that we deal with in engineering, and much easier to deal with strength materials than a big, blocky, deep member. But either way, let's say that this is like a beam or a column or a shaft. When I say cross section, I'll often abbreviate it X sub S, and that means that it is oriented 90 degrees from the longitudinal axis of a member. A cross section is just a specific section cut that's acting 90 degrees from the longitudinal axis. A section cut can be at any angle. So cross section is specifically orthogonal to the longitudinal axis, and just a section cut in general can be at any angle that you want. I usually mean to say section cut, but when we get into chapters 4 through 7, we're always going to be taking a cross section cut for the most part from there on out. But I just want to make it clear what the differentiation is between those two different things. So let's talk about average shear stress. So just like with the average normal stress, we're making some assumptions here. Um, the biggest assumption being a uniform stress distribution. So let's take a look at these blocks here. We've got a rectangular prism on top of two other supporting prisms. And the question would be, if we push down with this force F, how much shear stress will we get on these sections here? So you can imagine, and actually, yeah, the next diagram right here basically shows what the forces will be on each of these faces. So we can do basic statics. Again, I would make a free body diagram. I would show a coordinate system. I would use equilibrium. And you can figure out probably pretty intuitively, and if not, go back and just refresh your memory, that each of these shear forces V will be equal to the externally applied force F divided by 2. Now we're not given geometry and everything else, but if we assume that F is acting in the middle of that block, that half the load's going to go to one side, half's going to go to the other. And again, I just want to point out here that like there could be a normal force on these faces too, but due to the verticality of that loading and the fact that these section cuts are vertical as well, there wouldn't be any normal force acting on those faces. So even though they're equal to 0 and we don't show them, you can, in the back of your mind, think about every time that we make a section cut, you can think about, you know, normal force, shear force, and eventually bending moment acting on those as well. So here there could also be a bending moment, but we're assuming that's equal to 0, and likely we're assuming it's equal to 0 here because it's such a small distance, and that's going to be relatively negligible. Either way, we're just focusing on the shear force for now. And this is a good diagram showing our assumption that the stress, that the shear stress is assumed to be uniform. Whether I'm at the top or at the bottom or at the middle of this section cut, the intensity of the shear force is going to be the same. Now that's a pretty big assumption, and it's actually pretty incorrect. Um, for a rectangular section like this, I'll show you on another slide, the average shear stress that we calculate as equal to V divided by A, that's actually about 50% lower than the maximum shear stress that that rectangular section will experience. But e even though we still use average shear stress a lot in design calculations because we know what that difference is for specific shapes, but this assumption, it helps us with the calculations right now, but in chapter 7 we're really going to sharpen the pencil and figure out that that's a pretty incorrect assumption. The stress distribution of shear stress is typically parabolic, it's not uniform at all. So not only is it not constant, it's not linear, and it is usually parabolic in one form or another. So like I mentioned before, the average shear stress V over A is a big approximation. For a pure rectangle section cut, the maximum shear stress is equal to 150% of the average shear stress, and we'll talk about that in a lot more detail in chapter 7. I actually derived the formula to make the function that defines that parabola. But for now, we're just going to go with the average shear stress, which you'll still see in design codes and things like that, but it is a very big approximation. Now, something else to think about in terms of shear stress, it's very important, and we'll see this come up time and time again in our derivations, is that if we're looking at a state of plane stress, so we call this plane stress, and that simply means that we're talking about a 2D system. So we could really simplify this down and just look at one face of these elements. Actually, we just need to look at one of them. The whole point here is that if we have a shear stress acting on one face, we will always see the shear stress equal on all the other three faces. And the reason, like the y here, is statics for the most part. So let's look at what would happen if we put a shear stress on this face right here. The question is, could this element, I know it's differentially small, but just think of these stresses as if they're forces, because of this differentially small scope, it doesn't really have a difference between the two. If I have just that shear stress going up, I wouldn't be able to satisfy the equilibrium equation, the sum of the forces vertically equals zero. I'd have an unbalanced force. And so to get that to meet equilibrium, I would need to then provide another shear stress to cancel it out. The only other place that I can put that shear stress would be on the opposite face. That's the only other place that a shear stress is going to be acting vertically. So this takes care of the vertical equilibrium issue, but now I've got a problem with my moments basically. So now the shear stress on the right is going up, the shear stress on the bottom, on the left is going down. It wants to rotate this thing counterclockwise. And so in order to prevent that from happening, I have a couple different choices. I could put a shear stress on the top here equal to 2 times tau, but that's not really going to work because then my horizontal equilibrium is not going to be equal to 0. So just adding 2 times the shear stress on the top isn't going to work because I need to have horizontal equilibrium satisfied as well. So instead, I'm going to split that and put half, just put tau on the top and tau on the bottom. And so now everything is satisfied. Moment satisfied, horizontal and vertical force equilibrium is satisfied. And so that's why we have what's known as the complementary property of shear stress and shear strain. We'll see eventually. It's that um, once you induce a shear stress on one side of your differential element, it will automatically go to the other three sides in this kind of distribution. And we'll see this with the shear strain. We'll actually see the geometry change of what a shear stress is trying to do to these differential elements and see how it deforms. But this is a very important thing to remember, the complementary property of shear stress. So here's a good example, and we'll have a video, worked out video for this as well too. So this is combining the two different topics. So here we have an example of like a weld acting on, that's combining two different plates. We've got this weld, and you can see that it's oriented 30 degrees from the vertical is the side of that weld, and it's asking us to determine the average normal and average shear stresses on the face of section AB. AB is aligned with that weld itself. And so if we look at this from the side, you know, we're basically looking at, here's section AB, and we've got 50 kips going off to the left. And then to calculate the normal stress and the shear stress, we need N, V, and A. And so A is relatively straightforward. A is just going to be the area of that cut, that section AB. It's a little bit tricky. I mean, it's not just 2 inches times 6 inches. We've got to use trigonometry to get the modified, you know, depth of it. But that's relatively straightforward, just a little bit of geometry. And then for N and for A, well, we've got internal normal force. Let me change the colors here. We've got an internal normal force is acting perpendicular to that section cut, and we've got an internal shear force V acting parallel to that section cut, we've got a little bit of geometry to deal with here, right? We know that this angle is 30 degrees, but it's just a bit of trig in this problem. Other than that, it's relatively straightforward. And so you could imagine here, as that angle, if it wasn't 30 degrees, if it was 0 degrees, then we'd have all normal force and normal stress, no shear force, no shear stress. As that angle gets bigger and bigger and bigger, right, we see a lot more shear stress than normal stress, and eventually, yeah, it limits out as well too. So take a look at that video solution to kind of walk through a good comprehensive example that does both average normal stress and average shear stress. All right, and then a couple other points, one about single and double shear, one about factors of safety and allowable stress. Here, just want to point out, because we have a couple examples out of the book about this, the idea of single or double shear is if you're transferring a force from like one element to another through an intermediate piece, like a bolt, like you see in this diagram, like here we have a bolt that's connecting two different plates. If we have some force in here, it's transferring that full force through the bolt along like this shear plane right there. Here, the force, the shear force in the bolt equals F for the top example, which is what we call single shear. There's only one shear plane that that force is going to be going through. However, with the double shear example below it, with that force, half of it will go through this top shear plane and half of it will go through the bottom. And so even though the shear area is the same, there's now two of them, and they're basically just taking half of the force to the top, half the force to the bottom. So the shear force that we have to look at in the bolt is going to be equal to F over 2. So single versus double shear. Double shear is great. It's a much more efficient way of using bolts. But it just goes down to the fundamentals of what we talked about before. Shear stress is equal to V over A. Whether you're looking at half of the shear force or double the area, you get the same result in that the shear stress gets cut in half when you have a bolt in double shear as opposed to single shear. And that's what these kind of poorly reproduced graphics are showing you, the same exact idea. This is single shear, this is double shear. Either you're doubling the area or you're cutting the force in half. Either way, the effect is that the shear stress is cut in half for a double shear bolt as opposed to a single shear bolt. All right, and then the last thing that I want to talk about is this idea of allowable stress. So allowable stress is kind of our first foray into a discussion of factors of safety. So the idea is that if we have a material that we're pretty confident is going to fail at, for example, 50 KSI, which is a common strength of structural steel, if we're pretty confident that's going to be the failure stress, we don't want to take it all the way to 50 KSI under our regular expected loads. So let's say that you do your analysis and you find out that the due to cars driving over your bridge, that your beams are going to get to a stress level of like 49 KSI, and you know that they're going to fail at 50, or you're pretty confident of that. That's not a good design, because what if a truck drives over the bridge that's a little bit larger than what you expect? There's no real factor of safety there. And so what we do is, one way to deal with this, and there's many ways to do it, is that we'll incorporate a factor of safety that basically says we're not going to design this structure to go all the way to the failure stress of the material. We're instead going to take the failure stress, divide it by a factor of safety. That will give us an allowable stress that we will then limit our design to. So if we have a 50 KSI failure stress and a factor of safety of 2, then our allowable stress is 25 KSI, and that's the maximum stress that we would allow our designs to go to. And that means that we could have a couple of different scenarios. We could have a loading that's twice as much as we expected, and the system still wouldn't fail. or we could have really weak materials, like half as strong as we expected, and then it also wouldn't fail, or some combination of an overload and an undercapacity scenario, and we still might not fail the system. So this is the simplest way to kind of describe how we incorporate factors of safety to deal with uncertainty in our designs. If you get into a material design class, there's much more specific ways and like precise ways to go about this. This factor of safety kind of lumps together the uncertainty in the loading as well as the uncertainty in the material properties. In a lot of more sophisticated code-based design, we assign a different factor of safety for the material itself and then a different factor of safety for the loading itself. The loading basically increases the loads from our expected to account for uncertainty. The factor of safety on the material will drop down the strength to account for uncertainty. And it's all very specific to what kind of material are you dealing with, what kind of load are you dealing with. This is very much a shotgun approach where it's saying, hey, for everything lumped together, let's do a factor of safety of 2 or something like that. Your factor of safety always has to be greater than or equal to 1, otherwise you'd be um, uh, designing for stresses that are above your failure. But other than that, it's relatively straightforward. Um, yeah, so this is how we would simply use allowable stresses to calculate, for example, the maximum load in a system. So or like minimum dimensions of an element. So one way that we could use it would be if we know what the force in a bolt is in tension and we know what the allowable stress is for that bolt, we could then use it to back calculate the minimum area of that bolt. So being able to work through these problems forward or backwards, we know that normal stress equals N over A, and again, this should really be N for me to be consistent with what I was mentioning before. We know that that equation will allow us to calculate the normal stress based off the normal force in the area, but what if we have the stress and the normal force and we're trying to calculate the area? This allows us to calculate this equation can be used forwards or backwards, and the same exact thing applies to shear stress as well. There's an allowable shear stress you could calculate that would incorporate a factor of safety. You could then use that to calculate, for example, the minimum area of a bolt. And then here's a relatively simple example, actually very similar to the last example, but here instead we're using allowable stresses to calculate, kind of back calculate the maximum force P. So here we don't know what the force is. We're trying to calculate the maximum force this connection can withstand. And this involves, it gets a little bit trickier. And the biggest trick to this, and you can watch the video to really go through it, is we a common mistake that students make with this problem is that they would say, okay, well, I'm given my shear stress, I'm given my normal stress. I will then apply both of those to the bolt at the same time. However, we don't know, it would be very unlikely if the bolt would experience both the allowable stress in shear at the same time as the allowable stress in normal stress. These are limits. They're not saying that both of these would happen at the same time. This is like the maximum that either one can experience. So you need to look at two different scenarios. This is like a common design process. You look at two different scenarios. You set the shear stress to the allowable and then calculate P. You don't have to set what the normal stress is. Just set the shear stress to its limit. Back calculate P. That would give you one possible value of P that corresponds to the shear stress reaching its allowable. You save that. Then you do the same thing, but you set the normal stress to its allowable limit. Back calculate P. You'll have two different values of P. And then whichever one of those is smallest ends up being the maximum that the system can withstand. Whichever um, stress limit gets reached first will then fail the system, and that would correspondingly be the largest force P that you can apply to the system. So this is really getting into like design type problems now and looking at like different ways that a system can fail. Whichever one is the weakest link is what the capacity of the system is, and that's a very common thread throughout like a design process that you want to get used to. So that's the end of it for the introduction to stress. So take a look at those example videos when they're posted. 4 different examples to go over the basics of statics review, average normal stress, average shear stress, and then allowable stress, which they all kind of build on each other, but all good things to review. And especially if you're not feeling comfortable with the statics, chapter 1 in your textbook, I believe chapter 1, has a really good set of example problems to kind of refresh your memory about statics, free body diagrams, equilibrium equations, support conditions, internal resultants, all of that stuff. Again, I'm expecting you to be able to knock off the dust and rust pretty quickly. So make sure that you feel comfortable with that. All right, well, thanks for your time, and I'll look forward to talking to you guys about your questions related to this lecture. Feel free to reach out if anything comes up.